Hello everyone. Today I will show the solutions to problems 5 and 6 of round 166 of the Prairie Math League. For problem number 5, Bertha made some shots that were worth 4 points, 2 points, and 1 point. For the 4-point shots, she scored as many as the 1-point shot, like point worth, not like the number of shots, like the number of points she scored. And the number of successful 2-point shots was twice the number of successful 4-point shots. So this is actually not in terms of score, this is in terms of number. Overall, Bertha scored 49 shots. Again, this is a number. And how many points did she get from the 2-point shots that she made? So things can get confusing here. So it's probably best to represent everything in terms of variables. Let A be the number of 1-point shots, B be the number of 2-point shots, and C be the number of 4-point shots. Notice we're referring to number and not the points. Then basically what the problem is saying is, well, overall scored 49 shots, so A plus B plus C is 49. Since the point worth with the 4-point shots is equal to the point worth of the 1-point shot, we have this equation. This is the 1-point shots, and these are the points from the 4-point shots. And finally, the number of successful 2-point shots is twice the number of successful 4-point shots. That's basically this equation here. And now we just use this system of equations and solve. We can substitute, we can substitute this into here, and we get 7c equals 49, so c equals 7, and from this equation, b equals 14, and 2b, which is the number of points scored, is 28, which is option choice D. For problem number 6, we have 2 points on the circumference of a circle, let's say here and here, that are selected at random and independent of each other. From each point, a chord the same length as the radius is drawn clockwise. What is the probability that these two chords intersect? So suppose this is the radius. Then we take this length and do this to it, so they're equal. And here we see that no, they do not intersect. But as another example, you could have something like this and this. For this problem, we're going to fix one of the chords here for simplicity. We can easily achieve this by just arbitrarily choosing one of the chords and rotating it until the point happens to be here, so that the chord is like horizontal and the top. Then we can actually draw a giant hexagon. So the point being that when we have this thing equal to the radius of the circle, one very nice thing to do is connect these endpoints to the center of the circle, and notice that this forms an equilateral triangle. And similarly, you can proceed with the rest of the equilateral triangles below. But yeah, it forms a really nice hexagon, and it's quite useful for a lot of problems, including this one. For this problem, we're going to notice that we're going to have to choose the other point somewhere along this circle. And if we choose it in this region, this arc here, then we're guaranteed to hit, because no matter where we are, the next point, like the point that is 1 radius length away, is going to be on the other side of this point. So it's going to hit this chord. And on the other hand, if the point is in this arc, it's still going to hit, because if we go 1 radius length, we still end up inside this region here. So it is again going to hit the chord. But notice that in no other circumstances can it hit this chord. So it is only this region highlighted in green here. I guess it's kind of hard to see now, but it's only this region that is able to hit this chord that we selected, this top chord that we selected here. And this region is exactly 1/3 of the circle, again, because we can notice this because of this configuration. These are 60 degrees, 60 degrees. So the total angle here is 120 degrees, and 120 degrees divided by the full 360 is 1/3. Which is option choice E. And we're done. Thank you for watching.